Hello everyone. We now will explain the code for economic dispatch and demand response using particle swarm optimization in MATLAB. This code contains 5 files. Each file makes some functions. The first thing, we will load the input data. The input data file contains the solar profile and wind profiles for the case 1. And after that, we decide the number of decision variables. The decision variables contains 3 generations and the power from the network and the power demand response from the customer, 3 customers for the generation from 1 to 3, and the network power and the customer from 1 to 3. And after that, we define the minimum for each and decision variables or for each generation, and maximum for each generation and customers after define maximum and minimum regions. Also, we define the ramping upper ramp and down ramp for each generation and the maximum iteration number of iteration 600 and the population size or swarm 300. After that, we initialize some parameters of PSO optimizations here, and after that we also define some velocity limits for PSO optimization and initialization. The position particles cost of velocities best cost best position for optimization PSO, and after that define also global best cost and particle best cost. After that, we now define the initialized position initialized position for 24 hours for particles each position, and this is uniform round of the position. After initialize the position, we make or apply the load function. The load function, the main object of the load function here is to apply two constraint. The first constraint is the load equal generation plus wind and PV power minus demand response customers, and another object for this function for apply the constraint of upper ramping and down ramping. If you will see here in the load, the code, that is first thing, table 2 contain 2 things. The first thing is the load in each hour, and the second thing is the cost of energy in each hour from the network or if you customer curtail. And after that, the table 3 is contained wind profile and solar profile, and here defines upper bound of the generation and customers and lower down upper and lower bound of each generation and customer, and also defined upper rates, ramp rate and down ramp rates. After that, we applied the constraint for that the load should equal generation plus wind and solar profile minus demand response. And this is also applied for the upper and lower demand, lower ramp rates. After that, we finished the load profile. We get a new position. After initialize the position here and go to the, as mentioned before, go to the load, and the output from the load function a new position that achieved the constraint of the load equal generation and the lower and upper ramp rates. After initialize that of the position, we initialize the velocity of each particles by zeros, And after that, evaluation, the object function, economic dispatch and demand response. As you see here, this function contained the table 1 is load and cost of energy in each hours, and also load and wind profiles each hours, and after that initial parameters for the generation and the customers for the demand response. And after initialize the parameters, we applied the total load should be equal to generations minus demand response. After that, apply this function, we calculate the cost of conventional power here, this cost for generation conventional power plan, and this is for the cost of the networks C2. And after that, calculates the cost incentives and the cost of customers and applied in the fitness function with the weight factor 0.5. After calculate the economic dispatch and demand response here. Now we calculate, we get some cost of particles and the cost of incentives, the cost of customers, the cost of generation and the cost of networks. And after that, we calculate the cost of customers and the cost of network for 24 hours. After finished 24 hours, we applied the constraint. That constraint talk about the incentive scores should be less than 500, and also calculate that a customer energy that should be less than the upper or lower limits. After applied this constraint, we update the global best. The global best is the best cost we calculated ever in each or all particles, and update the position of the global best costs and the global best costs also, and the customer cost in this position that get the minimum costs. And after that, we start the main loop for PSO and start from the 1 to 600 iteration and repeated that this loop is contained the first thing after calculate the best positions. We update the new velocity for each particles, and then after updated the velocity, we applied the limits of the velocity should be less than a point minus 0.25 for velocity maximum and velocity minimums. And after that, after applied velocity limit, we update the new position. After update the new position, we applied also the position of limits that should be less than the maximum for each variables and the minimum. And after apply the limits on the position, applied the load function to achieve the load equal generation constraint, and then the upper and lower demand ramp rates. After applied this load against the new position that achieved the upper and down ramp rates and the load generation constraint, we evaluate a new object function or fitness, and by applied on new position in economic dispatch and demand response functions, and get the new cost for each position, and the cost of incentive, the cost of customer, costs of generation, and cost of network. And after that, after calculate for 24 hours, we applied the constraint for incentive of customers less than 500, and the energy from the customer should be less than the maximum energy should be curtailed. And after that, we have two things. First thing, update the personal best For each customer, we compare the best position in each particles with the new cost for the position. If the cost of the new position is best than the cost of the particles of the best cost particles, we will update the new position for the best for particles and the new best costs, and as a personal best cost for each particles, and for each particle. And after that we also update if some particles less than the global best costs, and we should update the best global best position and the global best costs and the cost, and save the cost of customers and generation costs and network cost at the global best cost, and then display the best cost in each iteration. And after that we repeated this function to a 600 a time, and after that, after finish the maximum iteration, we memorize the global best position in the solution and display the result. Display the generation 1 and generation 2 and generation 3 and the network power and the curtailed energy from x1, x2, x3, customer 1, 2, 3, and the load or generation from wind and solar in each 24 hours. And after that we make some plots for the best cost with the iteration and power curtailed from the customer 1, 2, 3, and the power from generation units 1, 2, and 3, and the power from the network and wind and solar with the time. And after that we display the total conventional power costs and the total transferred power transaction cost and the total the customer incentive and the total customer energy curtailed and the total unconventional energy curtailed generated and total transferred energy kilowatts. Now we need to explain the Dragonfly algorithms, code for demand response and economic dispatch, and the same thing that is here, the maximum iteration and the input data. The input data contain that wind profile and solar profile, and after that initialize the upper and lower limits for each customer and generations, and the number of search agents also initialized here and also in variable size. And after that we initialize some variables for DA algorithms here, for food fitness and enemy fitness and enemy POS. After that initialize that position for each search agents, and also initialize the another position for each search agents, and put it to the fitness 0 for each agents. After that we start the loop here from 1 to maximum iterations and define some variables for DA optimization. And after that we initialize start from the agents, and then initialize the customer energy, customer costs to a total generation costs, total network cost. After that we apply the load. As I mentioned before, the load is a function to apply the load generation constraint and the ramp rates constraint. And after applied this load function, we get a new position that achieved the 2 constraint. After that we calculate the demand in economic dispatch and demand response, as mentioned, as explained before, and the output of this function, the costs, fitness function, and the customer incentive cost of customer generation cost and network cost. And this is applied for 24 hours. After finished 24 hours, we applied constraint of incentive cost less than 500, and that energy from the customer should be less than the upper or the maximum curtailed energy can be achieved after calculate the demand responses, economic dispatch and demand response. We update the fitness, the food fitness. If the food fitness is less than the fitness, now we update the food fitness. This is the best position main food fitness, it's the best position, and update the value of food fitness and the value of the position and the value of cost, customer and generation cost and network cost. Just save it. And also the enemy is opposite of our food fitness. After that, we now compare between the new position for the search agent and the previous position, and if the sum limits for that to apply on it. And after that, after applied this algorithm of enemies and calculate the new position by using this function to calculate the new position of the next iteration after, and the new position of the delta x. After that, after finishing that, we put the best score equal food fitness and best position equal food be assumed. After finished that iteration or loop, we display the result as I mentioned before. Now we want to explain the case 2. The case 2 for economic dispatch and demand response, it is the same as case 1, but that the data is different or that an initial parameter is different. Now the first thing is the load, the input data, and the input data as mentioned before, it's contain the wind profile and solar profiles, and then put it the number of decision variable is 18. We have 10 generators and 1 network connection and 7 customers. And here we mentioned P2, P1, P2, P3 to 10. This is for conventional generation, and PR for the network, and this is X1, X2, X7 for the customers, and this is that a minimum and maximum bound, upper maximum bound for each variable. And also we define the up and down ramp rates for each generation for 10 generations. And after initialize that and put it the maximum iteration 100 and the number of population size 600, because there is a lot of variables and decision variables, so we need more iterations to get the best solution. And after that, we defined the PSO parameters and velocities and initialize particle cost and global cost. And after that, we initialize the position by randomly and uniform randomly. And after that, applied the load for the load function. The load function, as I mentioned before, is then to apply 2 constraints. The first one is the load should be equal the generation minus the demand response plus wind and solar profiles, and another thing to apply the upper and down ramp rates. After applied the load function, we achieved we get a new position that achieved two constraint and initialize the initialize the velocity equals 0 for each particle, and after that we calculate the demand response and the economic dispatch functions. Objective function as before. Here the function and we calculate the cost of and here we initialize parameters for each generator for each customer, and after that we calculated the cost from the conventional power and from the networks, and after that at the customer incentives, customer and cost of customer, and after that put it in the fitness function with weights. This is the weight 0.5 for each customer for each function, and after calculating this function we get it the best cost and the energy from each customer for 24 hours and the cost of the customer for 24 hours. After that, after finishing the 24 hours, we applied the cost incentive, the customers incentive cost. Customers should be less than 150,000 US dollars, and apply that each customer should be less than the maximum energy can be curtailed. And after applying two constraint, these two constraint, we updated the global best cost by compare with the global best cost with the best cost for each particle. If the best cost for each particle is less than the global best cost, we updated the global best position and global best cost and save the customer cost. And after updating the global best cost, now we go to the main loop for the PSO from 1 to maximum iteration 1000, and make repeated all this function 1000. We initialize the generation from each customer, the best position cost, the customer costs, its total generation costs. This is initial for each cost, and after that updated the velocity depend on the global best cost position, and applied the velocity limit on the new velocities and updated the new position by the old position plus new velocity for each particles, and applied after that the best the position limit should be less than the maximum for each generation or customers. And after that, after updated the new position and applied the limits, we applied the load function to achieve two constraint for the generation equal load and the up and down ramp rates. And after applied that load, we get the new position that achieved two constraint that mentioned, and then after that we calculate the fitness function for economic dispatch, demand response, and get the position cost, the cost of incentive, the cost of customer, cost of generation, and cost of networks. And after that we calculate it for 24 hours, and after finished from the 24 hours we applied the limit for total customer incentive costs for each day, and 150,000 US dollar. And after that we applied also the total energy from each customer during the day, and after applied to constraint, we updated two things. The first thing is the personal best position for each particle. For each particle, we compare with the best cost reached from each particle with the new cost of the particles. If the new cost is less than the best cost of each position, we updated the new particle position, particle's best position, and best position cost for each particle individually. And after that, we also updated the global best cost for all the position by comparing with the previous global ones. Best cost with the new best cost. If the new best cost is better than or minimum the less than the global best cost we updated the new position for the global best cost, and the global best costs also updated, and after that saved the customer cost, total generation cost, and the total network costs, and then displayed the new best cost for that iteration. After finished from the top and repeated this procedure, we put the best solution, we put the global best costs position in the best solution, and after that we displayed the results. The result is contain 10 generations, the network, the customers in each the customers, and the PV and wind or solar profile. And after that we also plot the best cost with the iteration, the customer power curtailed from each customer with the time, and the generation power with the time, and that the network wind solar power with the time. And after that we display the total conventional power costs, total transferred power transaction cost, and total customer incentive, additional that to the total customer energy curtail, and the total conventional energy generated, and the total transferred energy. Thank you for the listening. I hope we define all the cases and the DA case to the same thing